Hi. So to this point, you've learned about what an atom is and what parts make up an atom, subatomic particles that do, and then also about how do you calculate the number of protons, neutrons, electrons in an atom, and also what an isotope is. And a thing you're going to do now is talk about how each atom has a unique electron configuration and what that means for how the atom operates and what kinds of reactions it undergoes and that kind of stuff. Some of these things you won't need to write down. Be sure to let you know. In the first lecture of the week, we talked about how the model of the atom is kind of like a Jimmy Neutron model, where you have, sometimes it's called the planetary model, where you have the nucleus in the center and you have the electrons sort of zipping around it. And that's a good model, but it's not quite accurate for what's going on with the model, with the atom. And the person responsible for really determining a more accurate model of the atom was named Niels Bohr, and he did this around the turn of the century. And according to his model, electrons have to be certain distances from the nucleus, and each distance corresponds to amount of energy that the electron can have. And he sort of revolutionized what modern chemistry was like and what we knew was possible for the atom. So the electrons that are close to the nucleus are said to be in the lowest energy level, and the further away you get from the nucleus, the more energy level the electron occupies. So the farther away the electron is from the nucleus, the higher the energy level that it occupies. And those differences, if you ever heard the word quantum before, those differences actually, before Niels Bohr, we thought that could be any distance, but he determined that actually there's a small difference for each of those levels, and that distance is known as a quantum of energy. It's actually a measurable amount. So what he came up with was the quantum model of the atom. And I should preface everything I'm about to say by saying this, that the atom, as you can imagine, is extremely complicated. On the first lecture, we talked about the strong force, which holds the atom together. But you also have the electrostatic force of positive and negative attracting each other. Well, it gets even more complicated because an electron, because it weighs basically nothing and is also moving at the speed of light, like regular conventional physics don't apply to it. So you have to use quantum physics, and this seriously complicates what the atom looks like. So, which is, beyond the scope of this class, obviously, but because we're not going to get into doing calculus and calculating where the electrons are, but that's why it's so complicated, is because the electron's very small and has no mass and is moving at the speed of light. So the present-day model of the atom takes into account that the fact that the electron not only acts like a particle, like rotating around the atom, the nucleus, but also it's a wave as well. So imagine if you threw a baseball and it travels on a straight line path, but if the baseball was also doing this when it traveled, this makes it very hard for you to calculate where the baseball will be. And also you're throwing at the speed of light, so it's a pretty good throw. Instead of the electrons being located just somewhere outside of the atom, and you should write this down, they're instead located in orbitals, and those are regions that correspond to specific energy levels that are calculated by quantum mechanics and quantum physics and calculus. So we would never obviously do those calculations, but instead of us saying like the electron simply orbits the atom or the nucleus, what we're saying is that actually we don't know exactly where it is, but we can predict with a fair amount of probability it's going to be in a certain space, and we call those spaces orbitals. And the orbitals have these super complicated shapes where you find them, so we don't need to get into them. Some of them are like spheres, some of them are like flower petals, but the idea is that you can calculate where the electrons will be with a fair amount of certainty with some extremely complicated calculations. Kind of like, have you ever seen a distribution of a bell curve? Like, for example, the ACT, like, most people get, I don't know, whatever it is, 23. But then some people get a 34, and some people get a 4. I hope you don't get a 4, but you get the idea, like, not a lot of people get the extremes. It's the same with the atom. It's all probability where the electron is going to be. It's all about calculating where it's most likely to be, and then where it for sure will not be. So those places are called orbitals, and sometimes you call them electron clouds because they have, like, they don't have exact boundaries. Like I just said, we know it's going to be most likely in the center of this electron cloud, but sometimes it can be towards the end of it, and so the boundary is kind of fuzzy. If the electron is in its lowest energy, so the closest to the nucleus, we call it the ground state, and that is those two things say the same thing. So yeah, the closer the electron is to the nucleus, we call that the ground state. Is the lowest possible energy state. Now you can put some energy into an electron and then it'll jump up to an excited state. We call that, guess what, the excited state. And you can put energy into an atom by shooting a laser beam, running electricity through it. There's lots of different ways. But this is how you can move an electron up to a different energy state. And then again, that says the same thing. So an excited state is just where you have the atom has more energy than it does in the ground state. So who cares? Well, actually, you notice this all the time. This happens in lots of different cases where you can put energy into an electron and it will jump up to an excited state, and then it doesn't like to be there, so it falls back down to its ground state. And when it falls down to its ground state, it gives out some of that energy that you put into it. This is how fluorescent lights work. So when I flip the switch, like in a classroom, you know those long tube lights, electricity excites the electrons in the tube. There's a gas in the tube, and so there's a bunch of atoms in there, and the electrons are excited with the electricity, but they don't like staying there for very long, and so they fall back down to where they belong. And when they fall back down to where they belong, the electrons give off light, and this happens trillions and trillions and trillions of times every second with each of the atoms. And so what the net effect is that like horrible nightmare light that you see in my classroom or wherever else. So it's very common. If you've ever seen like a neon sign, same thing. It's not always just neon in there, but different gases, you run a current through them, and then the cool thing is that each element will give off its own unique wavelength of light. So we call them neon signs, but not all of them are actually neon. There are a bunch of different gases that give off different colors depending on what the atom is. So that is how the electrons fall back to their ground state. So each element of them, I think I already said this, gives off its characteristic wavelength of light. So each element is different. This is also how, like, when astronomers look at stars, they can tell what kinds of elements are in the stars or what kinds of elements are in the planets by the light that it gives off, because each element gives off its own unique wavelength of light. And I mentioned this is how fluorescent light bulbs work, and I'm going to show you some demonstrations in class sometime to give you some examples of different elements and what they look like. Okay, so this leads us to electron configuration. You can, if each orbital is like a region where the electron most likely is, you can sort of write out its own electron configuration for each element. And I already said all these things, but each orbital is based on probability, and it has their own unique shapes and sizes, which we don't need to get into. All these transitions. So the arrangement of the electrons around the nucleus can be shown by electrons or the atom's electron configuration. So each atom has its own unique electron configuration. I would write that one down because that's a definition of what electron configuration is. And the configuration looks like this. For sulfur, it has 16 electrons. The configuration is written as 1s2, 2s2, 2p6, 3s2, 3p4. And we're going to, in a second, learn how to write those configurations out. And that's not important. Oh, I guess I could say that there's 2 electrons in the 1s orbital. This is the, I'll show you in a minute, but the 1 describes the energy level of the orbital. The s is kind of the shape. And then the 2 is how many electrons are in there. And we'll get into that in a moment. And when you write electron configurations, you are going to use this chart, which you can find at the bottom of this video. You can find in your weekly like update from me on that Google document, or you can even find it on Schoology. I'll link it there too. But you're going to need to use the electron configuration chart to write electron configurations, and we're going to do that right now. Hi, this is a copy of the electron configuration chart, and you're going to want to either save this to Notability, or you're going to want to copy it down to your notebook. It's the kind of document that you would use over and over. So saving to Notability would be slick because you do write stuff on it, and then it's easy to erase it. If you want to put it in your notebook, again, you're going to want to make sure that you have it in a spot, maybe write in pen, and then when you're using it, write in pencil so you can erase it very easily. So this is the chart you use to write the configurations. Early in the video, you saw that the configuration for sulfur, which has 16 electrons, this is a terrible electrons, 16 electrons. E minus is how you would write electrons. The configuration was 1s2, 2s2, 2p6, 3s2, 3p4, I believe. And make sure my math is right. 12, 16, yeah. So the way that you write this and what this all means, you use this chart here that you see on the left to write that configuration out. Let's first start with what everything means real quick. The 1 is the energy level, so that number is the energy level. You see them also here, that's the energy level. The S is technically the shape, the letter is the shape of the orbital. We don't need to get into what the shape looks like because that's beyond what this class is going to ask us to do, but that is what the shape of the energy level or the orbital looks like. And then the 2 up here is the number of electrons. This is getting way sloppier than I want it to be, but that's the number of electrons. And so that's what the numbers mean. So you're saying in the first energy level, there's an orbital that has a shape, which we call S, which is not important, and then the 2 electrons in there. And so you use this chart on the left to do that. So let's do that now. I'm going to erase this whole thing so you can see how it all connects in a second. So we have here, when you use this, there's 3 rules, and the rules at the bottom, they won't make sense. I think it's the kind of thing that you'd want to like just try first, and then the rules make sense. So this, you can imagine this sheet up here like a bucket, and so you fill the electrons from the bottom to the top, so from the 1 up to the top. So you fill empty orbitals first, then you pair up. You fill the lowest energy first. That's called the up-up principle. You don't need to know the names, but that's just like the principle of it, or the actual technical name. And then only 2 electrons can occupy a single orbital. Again, once I show you like 2 of these, you'll be like, okay, I get it. Shut up, Mr. Summers. So here's how it works. Let's take something like, let's say, oxygen. Oxygen has 8 electrons. And if I want to write the configuration for oxygen, I use this chart here, and you sort of, like I mentioned, fill up the this chart from the bottom here, okay? So you start there and you fill up 8 electrons. Now, you can represent the electrons with lines. You can represent them with arrows. For reasons that you don't care about and are not really super important to this class, they tend to represent them with half arrows. Look like this. That's 1 electron, and then another one looks like that, another half arrow. So each one of those represents 1 electron. Electrons have spin, and they spin up or spin down. It's not important for the class, but that's why they're usually paired like that, because one spins up and one spins down. If you wanted to draw 2 lines to represent 2 electrons, that's fine. If you want to draw 2 arrows like this, that's fine, whatever you want to do. But I need to have 8 of them on this diagram. So what you do is you fill from the bottom, and each line here, this is an orbital. Each orbital can hold 2 electrons. So I've filled in with 2 electrons there, and I'm going to keep going. And again, the rules are you fill empty orbitals first, you fill from the bottom, and only 2 electrons per orbital. So starting at the bottom, I've drawn 2. Now I have 4, 2, 4. And then technically they go to empty orbitals first. So when you're here, I have to have 4 more lines, right? So instead of pairing up, they go empty spots first. Here's an empty spot. So 1, and then 2, and then 3. And then they pair up. That's the rule. And so now I have 8 electrons here. I've got 2 here, 2 there, and then I've got 4 total in this section. So 2 plus 2 plus 4 is obviously 8. So then when you write the configuration is just reading what you've written. So like this chart on the left is just to write the configuration out. So I have 1s, and I have 2 of them there. 1s here, and I have 2 electrons. That's what these are. And so I have 1s2, and then I move up. I also have 2s2. 2s, I've got 2 electrons in the 2s energy orbital or energy level. And then in the 2p total, I have 4. So I write 2p4. And there's your configuration for the electron configuration for oxygen. Okay, so all I've done is I've used the chart to write out the configuration. Like this is the work here, and then this is your answer here. That's the chart, that's the configuration. Let me erase some things and we'll try another one. Bye. Good enough. Okay, so let's try something small, like let's say, I don't know, silicon. So first thing is first is you want to find out how many electrons are in silicon. So you look at the periodic table and you say, oh, silicon has an atomic number of 14. So that means 14 electrons. And I'm going to use the chart and fill this up with 14 electrons. So I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, and I've used all the rules. I filled from the bottom first, which is here. Every line gets, or every orbital gets 2 electrons. I have mine 1 up and 1 down. It doesn't matter. You can just draw 2 lines if you want to. And then technically, although it's not super important for you guys, technically when they get to a spot like this, they go to empties first. So if I was going to add another electron, it would go here first because they go to empties before they pair up. Okay, so anyway, but each of these lines can still hold 2 electrons. So now if I want to write the configuration, this is the work for the configuration. And all I have to do is I read what I've written. So I have 1s2 again, and then moving up, I got 2s2, 2p6, 3s2, 3p, and there's 2 of them there, right? So 3p2 at the last spot. So the configuration for silicon is 1s2, 2s2, 2p6, 3s2, 3p2. Now remember, each of these describes energy level, and then the number of electrons in the energy level here on this part of the diagram. The line is the orbital, and then the 1 is still the energy level, number is still the energy level, and the S and the P and the D, if we get there, all of those are going to be the shape. Okay, so that's how they all match up. But remember, this entire part right here, that's all just the work. This is the configuration. If I was going to say the configuration to you, that's what the configuration would be. Let's try one more. Let me erase again. So close. So one more, we could do maybe a few, like let's do like nickel. So nickel is, and you should pause the video now and see if you can write the configuration out. Nickel has 28 electrons. So I'm going to fill it up 28, 2, 4, those guys, 3p, 4s, and 1, 2, 3, 4, that's the worst one ever, 5. I need 28. And I need 3 more. So there's my configuration for nickel. That's the work again. So if I was going to write it out, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d. How many do I have there? 2, 4, 6, 8. Okay, so there's my configuration for nickel. I hope you had the same. And you'll notice that in terms of energy levels, it goes 4s and then actually goes 3d. The 3 fills after the 4, even though 3 has a little bit less energy. Not really important, but this is a thing to remember, that when you're reading is left to right, that usually the numbers just increase, except when you get to the d's, then the number actually goes down by 1. Okay, so there's a quick primer on electron configuration, writing it out, what the chart means, how to use the chart, and we'll have another video that shows you some connections between the chart and the periodic table. But for now, this is all. This has been super fun. Bye.